Hey, welcome back again, everybody, to our statistics class notes in Chapter 9, our last chapter in the course. We're on page 137, and we're going to move into Section 9.2. So Section 9.1 was just a real easy introduction to what's going on when we're trying to infer about population means. And in Section 9.2, we'll get a little bit more into the nitty-gritty when we talk about the central limit theorem for sample means. So in this section, we want to be able to apply the central limit theorem for sample means to calculate some probabilities. And then we also want to describe the features of the t-distribution. Okay, so what's the central limit theorem for sample means say? It says that if certain conditions are met, okay, and these are down here, we'll go over these in just a second. They're very similar to what the central limit theorem for sample proportions was. But if the certain conditions are met, the central limit theorem for sample means assures us that the distribution of sample means follows an approximately normal distribution, no matter what the shape of the population distribution, which is quite amazing. Okay, so now it's going to be approximately normal, just like it was for the central limit theorem for sample proportions, and it actually won't quite be the normal. We won't be able to use the normal distribution. We're going to have to use the t-distribution, and I'll talk about that a little bit, but we'll say that, hey, it's approximately normal for now. Okay. All right, so central limit theorem for sample means, conditions to check on the result. So when determining whether you can apply the central limit theorem for sample means to analyze data, we need to consider the following three conditions. One, has to have a random and independent sample, so that's similar to sample means for proportions, that central limit theorem. Each observation is collected randomly from the population, and observations are independent of each other. We also have to have a large sample. Now, a large sample in this case means that, one, either the population itself is normal. So if we know that the population that we're pulling from is normal, then it doesn't matter what sample size we have. Any sample size is large enough. However, if we don't know about the population or it's not normal, then the sample size must be usually 25 or bigger. Okay, we need to have 25 or more. Okay, now for a big population, again, that's the same idea. Before, we have to have the sample being collected without replacement, so we keep independence, and then the population must be at least 10 times larger than the sample size. So that's the same big population requirement there. If these three conditions are met, then the sampling distribution of x bar, the distribution that x bar is pulled from, remember we will only have one of these, but the sampling distribution of x bar is approximately normal with a mean of mu, the true population mean, and a standard deviation of the standard error, which was the population standard deviation divided by the square root of n, which is the sample size. This sigma divided by the square root of n is called the standard error. Don't forget that. Okay, so note, the larger the sample size, the better the approximation. That makes it more precise. If the population is normal to begin with, then the sampling distribution is exactly a normal distribution, regardless of the sample size.